So in this series of lessons, and this is the last in that series, in this series of lessons, we've been learning how to do calculations with ideal gas laws. And I say it in the plural sense for this reason, that there's more than one law that deals with gases that have ideal behavior. There is the ideal gas law, but Charles' law and Boyle's law, Gay-Lussac's law, all those deal with gases that have ideal behavior. So this is the ideal gas law, the way we usually think about it. Hov-Nert, if you want to call it that. But there are some other things we can do with that. Let's use capital D to stand for density. What is density's two dimensions of measurement? Mass and volume. And how do we arrange those? Mass over volume, okay? All right. And for about 6 weeks now, we've been calculating molar mass. And what is molar mass made up of? What units of measurement, or what dimensions of measurement, either one, go into molar mass? Moles, okay. And what's the other part in molar mass? Mass. Okay, so let's use the symbol capital M to stand for molar mass. And the definition of molar mass, although we've always calculated in here such that we have the mass equals moles because it worked out great for us when we're doing stoichiometry, the actual definition of molar mass is the mass of a substance in 1 mole. And so that's mass per mole, okay? Mass per mole. And the symbols for mass, the lowercase m, and the symbol for moles, like in the ideal gas law, is N. Got that? All right. There are 2 things I want you to do. I want you to choose a learning partner to work with. I want you to do 2 things. 1, I want you to rearrange this equation to isolate N and then plug in what N is going to equal to in that isolated, rearranged equation for N right here. Well, actually 3 things, because then I want you to rearrange this. But let's do that first, okay? So rearrange this to find N by itself and plug in what N is equal to right here. Okay, so what I'm going to do here is I want to show you how to get N by itself. You can't leave N on the bottom of a fraction. Remember, you have to have it on the top of a fraction in order to solve for N, right? So I'm going to rewrite this equation. I'm just going to write it over here. Here's our molar mass is equal to mass per unit mole. I want to get N by itself, and I also want it on the top of a fraction. Okay, I don't want it on the bottom. So I'm going to multiply both sides by N over 1. Okay, so N over 1 on both sides, because if I do it to one side, I've got to do it to the other. And the reason I did it that way is so I could cancel N. All right, so I now have N on the top, but I want to get N by itself. Well, to get N by itself, I can put this over 1 and multiply by the reciprocal of this. Okay, and if I do it to this side, I've got to do it to this side. So now I can cancel this M, and I successfully have N all by itself. I've isolated the N, and I'm going to write it up so it's a little neater now. So I've got N by itself over here equals small m, which is the mass, over the molar mass. Okay, I'm just saying you got to show it. You got to show it so it comes out right every time. Okay, this is maybe a little bit longer way of doing it, but it's a way of being sure you got it right. Okay, this is what I taught. Do you have to do it this way? You do not have to do it this way. I'm trying to encourage you to do it this way because you're not going to get tripped up if you do it this way. If you show every step, you don't miss something. You don't assume something that's not true. Okay? So now I want to plug in this in place of the N here. Okay? So now I've got PV equals mass over molar mass times RT. Got that? All right, I want you to rearrange this equation now to isolate M. Rearrange this equation to isolate M. All right, so we've got, we want to get M by itself. So let's take and write this. PV over 1 equals mass over the molar mass And then RT we're going to put over 1. Okay? I want to get m by itself, so I've got to have it on the top of a fraction. So I need to multiply this side by capital M over 1 and multiply this side by capital M over 1. That's going to get the m by itself eventually. So this is going to cancel on this side. But now I need to get the m by itself by dividing both sides by the PV. And I can do that by 1 over PV and 1 over PV here. That gets rid of the PV on this side. And you have a new equation then when you put it all back together where the molar mass of a gas is equal to the mass times the ideal gas constant times the Kelvin or absolute temperature over PV. Okay? So this now is a new version of the ideal gas law. This is the ideal gas law, but it's just been rewritten so we can find molar mass a little faster. Here's a problem for you to solve. Now, let me ask you a question. What is the one thing that substances have that you know about that are unique to every substance? There you go. Now solve this problem. So, let's look at what we got here. We've got a volume of 79.7 liters. We've got a temperature of 22.0 degrees C. Bells and whistles should be going off because you should know that you can't use temperature in degrees C when you're doing gas laws, so we have to convert it to Kelvin. So 22.0 degrees C plus 273.15. And we have an empty slot on the right over here, so we know we have to round off a digit when we're done. So 295.15, and that is Kelvin. Going to round off this last digit over here, and we get 295.2 K. So this is also 295.2 K. We've got a pressure of 0.95 atmospheres. We've got a mass of 100.0 grams. And using the version of the ideal gas law that we just derived, this one here, we have the molar mass equals the mass times R times T over PV. So we still need to know what R is. We just want R to match the pressure units here. And the pressure units are in atmospheres. And so R that has atmospheres in it is 0.0821 liters times atmosphere divided by moles and divided by Kelvin. 0.0821 atmospheres times liters, or liters times atmospheres, over Kelvin, or times mole, or mole times Kelvin. Okay? So we have everything we need to plug in here. So molar mass then, M, is equal to the mass, 100 grams, times R, 0.0821 atmospheres times liters over Kelvin times moles. T, the temperature, the absolute temperature, the Kelvin temperature is 295.2 K. I'm going to put all of that over pressure, which is 0.95 atmospheres, 0.95 atmospheres, and times the volume, and the volume is 79.7 liters. Okay? This is a mixed fraction or a complex fraction, and I think in your math classes they say you resolve a complex fraction by multiplying by the reciprocal. Well, to have a reciprocal, we need to put these things on the bottom over 1, and it would be a lot easier if I put these over 1 as well, just to make everything kind of work out nice and neat. Now, you can actually skip this step if you know if you can look at this and see, that's what I'm going to do. So if you skip this and you end up with just this, that's fine with me. I'm sorry, that should be 100, not 1. 100.0 grams over 1 times 0.0821 atmospheres, liters over Kelvin moles, 295.2 K over 1. And we're going to invert multiply is what I like to call it. So we're going to flip these on the bottom and multiply over here. So we're going to have 1 over 0.95 atmospheres and 1 over 79.7 liters. Okay. Now we're going to do the dimensional analysis and check the units and see if we come up with what we need. So grams don't cancel, nothing on the bottom with grams. Atmospheres, I've got atmospheres here and here, those can cancel. Kelvin cancels here and here. Moles don't cancel. Liters do cancel. And so what I'm going to end up with is grams per mole, and molar mass comes in units of grams per mole. Okay, so you guys have already done the math, right? Tell me what the unrounded answer is here. And that's grams per mole. Going to round that off to 3 significant digits, or 2 significant digits, right? Okay. And so we get 32 grams per mole. And the question is, what is the gas? Well, the gas that you guys have all dealt with quite a bit in here that has molar mass of 32 grams per mole is oxygen. Oxygen is O2. Since the atomic mass of oxygen, the atom, is 16.00, you have 2 of them, so that's 32 grams per mole. That make sense? So this is the answer here. There's our answer. Because oxygen is O2. The atomic mass on your periodic table for oxygen is 16. And so the molar mass is twice that because it's O2. That makes sense? We just used it a lot. I hope you would figure that out. Any questions about that? Because this is the number that has the least significant digits. That's 2 significant digits. So we're going to round our final answer to 2. Okay? Any other questions? Okay. Let's go back to our rearrangement here of those equations a minute ago. Okay? Because you notice I listed density up here a minute ago. Okay? So density is mass per unit volume. Do you see mass and volume over here somewhere? Can you rearrange this to get mass over volume by itself? That is, I say isolate mass per volume. Please take a minute and do that. Rearrange this to get mass over volume by itself. Isolate mass over volume. Which will be the density? We want to get mass and volume by itself. So if we have molar mass equals mRT over PV, and I want to get rid of the RT on this side, I want to divide by RT. So if I do it to this side, I've got to do it to this side. Divide by RT. I kind of left it blank on top because I already know that to get M over V by itself, I also need to multiply by the pressure. So I'm going to put pressure up here. Okay? That allows us to cancel RT and P on this side and leaves us with MV. Okay? So now P, pressure times the molar mass over the ideal gas constant times the absolute temperature is equal to mass over volume, and as we stated earlier, that is density. Okay? Huh? No, MP is the same as PM. Okay? I mean, for gas laws anyway. I know that MP stands for military police and PM stands for prime minister, but we're not getting there, okay? Okay, so what we're looking for here is this. All right, so there's a derivation of the ideal gas law. Still the ideal gas law, it's just rewritten so we can find density. So a moment ago we looked at, or there was some discussion about the Hindenburg disaster, and the discussion included what was used to make the Hindenburg float. Okay, that was hydrogen, correct? Okay. Well, I put on the board behind me the density of air, and we're going to compare the density of hydrogen, all right, at some rounded temperatures and pressures and things like that. So let's say we have, let's find that what is the density of hydrogen at 1 atmosphere, which is the average pressure at sea level, and let's say 25.0 degrees C. Okay? What is the density of hydrogen at 1 atmosphere and 25 degrees C? Since we're trying to find density, and we already derived a version of the ideal gas law where density is already isolated for us, kind of makes it easy. I hope it makes it easy. We have density equals pressure times molar mass over the ideal gas constant times the absolute temperature. Okay? So density is what we're trying to find. We have pressure is 1 atmosphere. We've got a temperature of 25.0 degrees C, but we can't use degrees C temperature, so we need to calculate what that is in Kelvin. So 25.0 degrees C plus 273.15. So 298.15, we've got this empty slot here. Can't put a 0 in there because that would indicate a degree of precision that doesn't exist. So this is Kelvin, but we need to round it off to 298.2 K. So the temperature we need to use is 298.2 K. And we need to know the molar mass if we're going to use this version of it. And we know that hydrogen in the atmosphere, or normal hydrogen, would be H2. Okay, so we're going to take the atomic mass of hydrogen, 1.008, and multiply it by 2, at 2.016, and that's grams of H2 equals 1 mole of H2. And for writing the molar mass, I shouldn't put a line into that, it means something else. Capital M, molar mass, is going to be written as this mass per unit mole. So 2.016 grams per mole. So we have everything we need for this version of the ideal gas law except R. So we need to figure out which R we're going to use. And we need to use the R that has atmospheres pressure. So we go to the reference over here and we see that the version of R that has atmospheres pressure is this one. 0.0821 liters atmospheres over moles Kelvin. And we're ready to plug and chug. So density is equal to P M per molar mass over RT. If you want to simplify it right up front in the front, you could do it like this and say that's P M over 1 times 1 over R and T. Then when you plug everything in, it's already inverted and multiplied for you. If you know how to flip this. I'm going to do it that way. I hope it won't confuse you. If it confuses you, let me know, and we'll redo it again, okay? So pressure is 1 atmosphere. and put that over 1. Molar mass is going to be 2.016 grams over moles. R on the bottom of our fraction just means we take this R here and flip it. And the temperature we said was 298.2 K, so we're going to put that on the bottom here. And we go through and check units here. This is the dimensional analysis process that helps us to figure out if we set it up right. So atmospheres are going to cancel, moles are going to cancel, Kelvin temperature is going to cancel. We're left with grams per liter, and that is a mass over volume set of units, so that we know we probably set it up right. That is a way of measuring gas density. Zero 82. More digits. 35928. 283 grams per liter. Let's see, I've got 3 digits here and 3 digits here, 4 and 4, so the number of significant digits we want will be 3 digits. These 2 zeros right here are leading zeros. They're not significant. These 2 zeros are significant because they trail both a decimal place and a non-zero digit. So that tells us we have 3 significant digits. These leading zeros are not significant. So 1, 2, 3, those are our significant digits. We round it off to 0.0824 grams per liter. Okay? And this is the density of hydrogen gas. So why do balloons, or in the case of the Hindenburg, why do dirigibles that are filled with hydrogen float? They're less dense. Okay, to say they're lighter is not really the whole story. It's really because they're less dense. Okay? Why do you float in the pool? Because overall you're less dense.